Okay, so that is a very general abstract framework, right? But now let me blow them up here. If I have this, that means I have the vector. The vector is linear combination of those basic terms. So that means I take this particular thing here just equal to that, multiply with that term, then multiply with that term, and so on. Right? And with that means I can write x n is equal simply summation in k, and I have 1 over square root of n outside, and I have inside here I have xk, and I have this thing here, the component of that is just e j 2 pi over n k n. Right? And now recognize this. It is a discrete Fourier transform forward. Right? And this part here, to find it, is just simply x k here is, if I take this inner product, write it out, it's just 1 over square root of n, and summation in k go from 0 to n minus 1. And I have here that taking the x n. But now I can incorporate conjugate with this, so that's why I see that sometimes we learn one have to be that, and the other one is minus j 2 pi over n by n. Okay. So the thing we want to put in perspective now, right? The discrete Fourier transform, okay, so this is nothing but, okay, maybe when you learn the you have 1 over n, one and no the other one, right? So let's put this square root and here, but it's easier to deal with. Okay, so this thing here is very important. Use all the time. This is called the discrete Fourier transform. Okay, this is Fourier transform, and it is so important that we have a name for it, DFT. Okay. And you might see the formula before. You see this formula before. What I really want you to understand after just this part here is understand behind the formula. What it simply means is you take a signal and now you look at that signal on the different bases. Right? The bases not just those components, but the bases are those ones. And the basic of those components, for example, the first one is just a constant signal. This one here maybe have some frequency, and you get higher and higher frequency. Right? So that is a key part here. And the Fourier coefficient that what we have here, what it's giving us here is how much of that particular frequency is contained in our original signal. Right? So that is a frequency analysis. And just give you an indication of how important this thing here is. People have this, and you know this. To compute it is very, very complicated. Right? Well, think about n squared operation. Right? You have n here, and you take n of those by n squared. Take quite a lot of time. And of course, we know that there's a fast algorithm to do that. It's called the fast Fourier transform. Right? Which is much faster, and it discovered around 65, and that people now contribute that is above DSP, because after that moment we can all carry this operation very efficiently. Okay, but behind that here, conceptually, it's just simply decomposition. Okay, any questions after this? All right. So, I don't have any questions. You have to do something that really make you to ask questions. How about I'm going to give you an exercise in the class? I want you to think about this. Okay. I want to okay, so how can I'm going to do this following thing. going to consider this basis. But let's see. So these operations is really mapping n number, another n number here. And the inverse transform is mapping n number back to this one. Right? And in the line graph is just a basic operation. So how about we think about the following? Let's see. Let me define the Fourier transform, and then delete them back later. So this signal only have me if I have only n sample signal. But now, for generosity, I'm going to define a discrete time Fourier transform. And that is the VTFT. I'm going to define this now. I have a signal xn, and for any real number. So I have a whole sequence of numbers here. And looking at this sequence here, so I take the same sequence xn and I weighted them with this complex exponential signal. And instead of restricting myself to only this thing, 2j, 2 pi over nk, I'm going to consider the transformation is, look at this function x, but now instead of only one sample, I have a whole continuous function. And I define that my definition is equal to summations in n, so from minus infinity to plus infinity, xn e minus j omega n. Who have seen this formula before? No? That's a new formula. Okay. But can you see that? Okay, I might use a mixed notation. Sometimes I use xn here, xn, the same thing, right? Maybe you should do one thing here. So this thing here, what happens is I take a sequence and I have another function. This thing is nothing but a generalization of this form. But now I allow the summation go all the signal and allow this thing to have any other value here, not just 2 pi n over k over n. Okay. Tomorrow we'll look at more closely at the limit. And I think today in the afternoon we have some exercise to see that. Now, I want to tie up with this, the early part of the lecture. I have this thing here, and I'm assuming that you know how to go back. I'm going back here, so that is the forward version of this. If I take this and I go back to the inverse versions, then I can take this xn here. If you want to take back, it's easy to show, but I want to show